or not. We just go like 1 or whatever.
Yeah. Would not be comfortable.
I don't know. I ain't trying to
Somebody
go
doesn't
down
really
that.
find out.
All right, so we're going to talk about exact equations and integrating factors. So last time, when we were talking about exact equations, just a quick recap. We have m of xy dx plus n of xy dy. We said that was 0. This is exact if and only if m sub y equals n sub x. And that was a result of the equality of mixed partials. So if it's exact, this is an exact differential, and these are the first partials with respect to x and with respect to y of some other function f of xy. And we can solve this. So we integrate m and n with respect to the appropriate variables. Well, we saw the first example we talked about yesterday. These partials were not equal. And I said we don't know how to solve those yet, or solve that one yet. So we're going to talk about what we do in that case, or what sometimes we can do. So if the equation is not exact, we can sometimes find an integrating factor. That will make it exact. All right, so we have two possibilities. The first possibility is if m sub y minus n sub x over n depends on x only. Then mu, our integrating factor, sorry, I'm having some lag here, mu of x equals e to the integral of this quantity that is an integrating factor. And multiplying through by our integrating factor, multiplying the entire equation by the integrating factor, will make it exact. Yes?
Like, what makes a quantity an integrating factor or not?
What makes it an integrating factor is, well, when we talked about first order linear, it made it an integrating factor because it turned the one side of the equation into the derivative of a product, which allowed us to integrate both sides. Here we call it an integrating factor because we multiply through by that factor, and it lets us solve the differential equation. So it turns the equation into an exact equation, so we can then integrate the new component functions to get our solutions. So it allows us to integrate to get a solution, basically. And if n sub x minus m sub y over n sub x minus m sub y over m depends only on y. Then mu of y equals e to the integral of this quantity is an integrating factor. And if you're interested in the y, it's not super complicated, but it's just a little talking about derivatives and what the function depends on, and multiplying through turns our equation we can substitute, and we end up with a separable differential equation that we can solve for mu, is the bottom line, if we use this integrating factor. And then once we have mu, we can multiply through by mu, and that turns our equation into an exact equation. It goes through it in the book. If you're interested in it, I can go through it as well. I have it here in my notes. It's not super technical, but it involves solving another differential equation that lets us find mu, and then substituting mu, or multiplying through by mu to make our equation exact. Yes?
What are the m's and n's in the denominator?
They are these. All right, so I just want to go through an example. In my experience, this thing doesn't come up that much, using this integrating factor, but sometimes it comes up. Y times x plus y plus 1 dx plus x plus 2y dy equals 0. So this is in the form of something that maybe could be exact. Often when we see our differential equation in this kind of differential form with these functions in front of our dx and dy, that suggests check if it's exact. So here I'm going to say m, I'm going to multiply through, is xy plus y squared plus y, and n is x plus 2y. Partial of m with respect to y is x plus 2y plus 1, and the partial of n with respect to x is 1. So this is not exact. Now, which of these things you choose depends. You can choose either. You try one, and if it's a function of x, this is a function of x only, you can use that. You try the other if it's a function of y only, try that. If you try the first one and it's not, this first one is not a function of x only, then try the other one. If neither of them work, then you're kind of stuck. For this particular one, just because I see this quantity, if I subtract I'm just looking at what I wrote here. which doesn't make sense. Because if I do m sub y minus n sub x, oh, that works, over n, that's why it works. I get, if I subtract these two, I get x plus 2y over x plus 2y equals 1. Which is a constant, which is a function of x only. A constant function is a function of, we could say it's of either variable, but I can say this is a constant of x only. So our integrating factor is e to the integral of 1 dx, which is just e to the x. And we know we don't have to worry about the constant with our integrating factor because we're multiplying everything on both sides of the equation. So I'm going to multiply the original equation by e to the x. So I get e to the x, xy, plus e to the x, y squared, plus e to the x, y, dx, plus e to the x times x, plus 2e to the x, y dy equals 0. And now if I check partial of m with respect to y, I get x e to the x plus 2 e to the xy plus e to the x. And n sub x is x e to the x plus e to the x plus 2 e to the x y. So now we have an exact equation. And I can integrate these component functions, this one with respect to x, this one with respect to y, to find my original function. So m with respect to x, we're integrating x e to the x y plus y squared e to the x plus y e to the x dx. Here we have an integration by parts. We get that y is a constant, so y x e to the x minus e to the x, that's the integral x e to the x, plus y squared e to the x plus y e to the x plus possibly some function of y. And we integrate n with respect to y. So we're integrating x e to the x plus 2y e to the x dy. And I get x y e to the x plus y squared e to the x plus possibly some function of x. And we look whatever functions of x are in this that are not in here are functions of x, whatever functions of y are in here that are not in here are this constant with respect to y, and we get f of xy equals xy e to the x plus y squared e to the x plus c equals 0. C is our scalar constant. Sometimes you can pick either of the things to do. Sometimes if they both work, Sometimes one works better than the other. The integration is nicer. If only one works, that's your only choice. If only one of the integrating factor possibilities works, that's your only choice. So let's see. For this part, the homework that has some integrating factors, what did I assign? The every other 1 through 13, every other odd, and 25? Is that what I assigned yesterday? So our homework is for this that involves integrating factors. This is 2.4. Number 27. 33, 35, 29, 33, 35, and 47. And I'm going to stop this video because I want to save this one separately.